When most people think of energy, they think of electricity. We use it to power our cities, power our homes, and most importantly, charge our cell phones. Since electricity is a secondary source of energy, we have to generate it from an energy source. Once it's been generated, it needs to be transmitted to your home, to your school. Let's understand the journey of the electron from the generator to your smartphone. Electricity is all about the electron. We know that atoms have protons, which are positively charged, neutrons, which are neutrally charged or have no charge at all, and electrons, which are negatively charged. Protons and neutrons are held in the positively charged nucleus of the atom. Electrons are found outside the nucleus. Electrons closer to the nucleus may be held more tightly because of their attraction to the protons. Think of it as magnets. The closer magnets or opposite ends of magnets are to each other, the stronger the force is. So those inner electrons are tightly held. The outer electrons are a little bit further away. That attractive force between the positively charged nucleus and the negatively charged electron is a little bit weaker. Understanding how the atom is held together helps us understand how we get this secondary source of energy. The electrons are found in these different energy levels, held on by that electrical force. We know that those electrons can be pushed out of their orbits by applying a force, just like you pushing on a wall, pushing on an object. They can move from one atom to another, creating electricity. So the trick is, if we can create a force that can push those electrons and get them moving, we get electrical current. Magnetic fields can produce the force to push electrons in metals that have loosely held electrons. So electrons that are in those outer energy levels, the ones that are further away from the positive nucleus, that can be pushed away easily by a magnetic field or a change in a magnetic field. Electricity and magnetism go hand in hand. They're related. You can't have one without the other. Every time a magnetic field changes, an electric field is created. Every time an electric field changes, a magnetic field is created. Think of it as three variables: motion, magnetism, and electricity. If you have two, you can provide the third. This is due to an important term called electromagnetism. It's the interaction of forces occurring between electrically charged particles that can create an electric field or magnetic field. So magnets can create an electric field. As this magnet changes directions, it pushes those outermost electrons in the copper wire through the copper wire, passing that electric charge along and therefore generating an electric current or electric field. You may have observed an electromagnet doing exactly the opposite. An electric current passes through a wire and it creates a magnetic field. We can practice this on a large scale when we look at generators and power plants. Power plants use turbine generators to generate electricity. So instead of moving the magnet by hand, these turbines act like giant windmills. High pressure steam, water, or wind pushes past those blades, past those turbines to get it to spin, just like we did with the magnet. A generator is a device made of coils of wire and magnets. One rotates inside the other. The rotor is the rotating component. The rotor rotates. It's attached to a shaft or a long pole that connects to the rest of the generator. The stator, which is the stationary component, does not move. It stays in position. Our goal is to get that rotor to spin. If we can get the rotor to spin, a magnet or copper wire will spin and induce or generate an electrical current. To get that rotor to spin, we need to put in that turbine. It's a device with blades, like we talked about, like fan blades, which is turned by a force, wind, water, steam, to convert motion energy into electricity. Many different generators start with a different source of energy, but they spin a turbine, spinning a rotor, held by a stator, which generates electricity. To look at that further, we can see that there's different types of power plants that essentially function the same exact way. Your basic thermal power plant uses thermal energy to create steam or high-pressure fluids to turn a turbine. If the source is burned, usually it's a chemical-based form or source. Coal, natural gas, nuclear energy, which is not burned but instead gives off energy through nuclear fission, biomass, petroleum, and geothermal, which is the Earth's natural heat. So quite often the material is burned to boil water. That water, it's now excited. Those molecules move faster and further apart. As they move faster and further, they turn into steam. They're more energized. They're going to push on that turbine, spinning the rotor, generating electricity. As that magnetic force pushes out those outermost electrons in the copper coils. If there's a natural source of heat, that steam can directly be put into the turbine. PV, or photovoltaic cells, which is a fancy word for solar panel. If this is radiant energy that directly turns into electrical energy. So in this case, we don't have a generator, we don't have a spinning rotor, we don't have a turbine. Instead, we have a process that directly turns radiant energy into electric energy. This is called the photoelectric effect. Of all the things Albert Einstein is known for, it's the only thing he ever won a Nobel Peace Prize for. He was slightly attached to a research study that helped find the photoelectric effect, which allows us to turn solar rays directly into electrical charges. The reason that's his only Nobel Peace Prize is everything else he ever hypothesized or designed could have caused damage. Not quite a peaceful scientific experiment. CSP, or concentrated solar panel, uses thermal energy from the sun. Mirrors focus that energy to a stream of water or salt, melting it. So it works very similar to a thermal power plant. That heat transfers through into either a turbine or is stored later and used to heat homes. If we don't boil water, if we don't need steam, we can use things like water or wind, motion energy that's naturally there. As water goes down a river or as it flows through a dam, wind flows through the air as it's unevenly heated on the earth. We can take full advantage of these freely moving air molecules and water molecules and put them to work for us. A wind turbine looks slightly different than a hydropower generator would, but they're the same idea. Water pushes on the turbine, wind pushes on the turbine. That spins the rotor in both cases. The stator holds it all together, and we push those electrons out, generating that electricity, that secondary source of energy. We know that in the United States we're very reliant on electricity, but where we get it is very important. Currently, about 32% of our electricity comes from natural gas. Coal comes in real close at 29.99%, and then followed really closely by uranium or nuclear energy. These are not only the biggest sources for generating electricity, but they're also non-renewable. Petroleum is a very small percent. The only place that you can really rely on seeing petroleum for generation of electricity, other than maybe a personal generator, would be Hawaii, a state where they do not have as many natural resources available in order to generate electricity. As we get down into the renewable side of things, we see that hydropower is at about 7.3%. So these are things like the Hoover Dam. Wind turbines are popping up all around the country. So 6.3% is a number that seems small, but it's always increasing. Biomass, solar, and geothermal are very small amounts. Solar and geothermal, a lot of times it comes down to location, location, location. As we look at the cost benefit, the pros and the cons of non-renewable versus renewable, things like technology come into play. Natural gas and coal have a lot of energy, very condensed energy, a lot of bang for your buck. Whereas technology hasn't quite caught up with solar. It's catching up with wind, and that's why we see a rise in it in our generation of electricity here in the U.S. and across the country. Once we've generated that electricity, we need to get it to the houses. We need to get it to the people. Electricity is easy to move, but it's easier moved in long distances at a higher voltage. So the first thing we do is we generate this electricity. No matter what the plant, we've got those moving electricity, or those moving electrons. To get that electricity moving at a higher voltage, to travel a longer distance, transformers step up the voltage. A certain amount of electricity is lost in transmission. Stepping up the voltage helps minimize this effect. It makes it more efficient. This is like when a bouncy ball comes to a stop. We could make that ball bounce higher. We can retain and waste less of that energy. Now that it's up to a higher voltage, it can travel along those big transmission lines. When it gets a little bit closer, the transformers have to step the voltage back down to get it safer. These are those substations you might see on the side of the highway. It then follows smaller lines, smaller transmission lines to get to your neighborhood. Still at a higher voltage to get to homes, businesses, schools. Once it's in your neighborhood, the transformers that you might see outside your window on the power lines will then drop the voltage down again to make sure it's safe to use in your home. And then to make sure it's even safer, as it enters your home, it's entered through a 3-wire cable monitored by an electric meter. From generator along miles and miles and miles of transmission line all the way down to your house. If you look at that map on the screen, you can see the path. These are the United States transmission grids. These are essentially the roadmap electrons travel throughout the United States, from one side of the country all the way to the other in some cases. Once the energy has arrived in the form of moving electrons, once you plug into the wall, you can start using that electricity immediately. That electricity is sent to you by a utility. The utility is the provider that generates the electricity. They may transport that electricity to you and or even maintain the lines. Lots of jobs, lots of roles go into this utility infrastructure to keep the electricity flowing round the clock. The utility sends you electricity so you can use electricity. When you use electricity, you're using a load. A load is anything that draws power. These are devices like electronics, cell phone chargers. At home, your TV, your light bulbs. At a business or at school, computers. In industry, these are any production equipment that may be needed to make something in a company. To keep these loads powered, to keep these devices full of moving electrons, we need to keep a certain level of base load power. This is power that's generated throughout the day, all day, every day, 24/7. It's the minimum amount of electricity needed to meet the needs of all of the consumers in an area. If enough energy is not provided, if enough electricity is not provided to meet this baseload power, we see blackouts and brownouts, and that's when the lights go out. Baseload plants usually operate near full capacity all day, every day. Now, there are some times throughout the day where you may instead need peak demand. This is when everyone's coming home for the day. This is when all the TVs turn on. This is when everyone starts charging their devices. If we just worry about the base load there, we might not provide enough. So not only are we always generating electricity, but we always have to anticipate the needs of the customers and provide energy when people really need it. This goes back to those smart monitoring of the whole grid network, monitoring how much you're using in your home, how much a whole neighborhood is using. Energy utility companies have to consider these things in order to keep the costs of energy reasonable and to keep the lights on. No matter what the source, we begin with our secondary source of electricity is all about that mighty electron moving. We get it moving with a magnetic force, spinning a rotor. That pushes it through an entire grid full of power lines at differing voltages to keep us safe, to help us monitor and make sure we have enough energy.